Hello guys, welcome to another video tutorial. In this video, I am going to solve the problem 20 and so on. Let's see how many problems we can solve today. So before I start, let me explain this. In the previous video, we had a typo error. Here the unit of the hysteresis loss, the unit of the area of this hysteresis loop is joule per meter cube. Okay, so we had this typo error. The power loss is the volume of the core. The unit is meter cube times joule divided by meter cube times 1 divided by second. So the unit will be in watts. So we had this typo error, and also one guy asked me about the hysteresis loop that we draw inside this. Let me explain this again. Here we have this hysteresis loop that is given in the problem. But when we calculate the maximum flux density in the core using these numbers given in the problem, as you know, we have a sinusoidal excitation, okay, and we calculated the value of the Bmax. Bmax is 0.188 Tesla. We don't reach 1.2 Tesla, so we cannot use this hysteresis loop. So what is the hysteresis loop in our case here, considering these numbers? You know, we had this figure in the reference when we have this coil core system, and when we have this excitation, suppose we fed this coil using a sinusoidal current. In this case, we will have these hysteresis loops, and when we increase the level of the excitation, actually the value of H max will be higher, B max will be higher, and so on. This is the normal magnetization curve. And as you saw in the ANSYS Maxwell and the BH curves that we used for soft irons, for simulations, just we considered the normal magnetization curve. This is an approximation, and this approximation is good when the area of the hysteresis loop is not too high. For example, for permanent magnets, right, we need to consider the hysteresis loop for the finite element calculations. Later I will show, because in that case the area of the hysteresis loop is high and we need to do the calculations considering the hysteresis loop. But for the soft iron, for faster simulations, we consider the normal magnetization curve. So here in this example, the Bmax that we calculated is equal to 0.188 Tesla. We can consider this normal magnetization curve, and if we excite the coil considering a lower number of H, lower than 10, for example this number, this is the trajectory of the the operating point in the HB curve for the coil core system. So this is the coil and this is the core that we have in this case. Consider this coil core system, and suppose we start from this state in the material, this state, the B is 0, H is 0. When the current starts to flow in the coil, we have increase in the value of the current, right? We move in this direction, then we reach this number, 0.188 Tesla. And this is the direction that we return, right? And so on. So considering the hysteresis loop that is given in the problem, we can find the Bmax and Hmax using this red line. Okay, we have the slope of this red line. What is the slope? Is 1.2 divided by 10. So we have Bmax, and then we can calculate Hmax and calculate the area of this rectangle. If we increase the level of the excitation, we will have this rectangle. If we increase more and more, and finally, when the value of H is equal to this one, we have this saturation, right? This saturation occurs, and we will have this hysteresis loop. This is important, and you should remember this important figure from the reference. Anyway, okay, problem 20. Figure P120 shows a two-winding transformer with a laminated core. The winding with N1 has 200 turns and it is connected to a voltage to produce a flux density in the core equal to 1.2 times sine of 377t. Yes, we have this time varying function, and the value of the flux density in the core is given here. The variation is sinusoidal. The maximum value is 1.2 Tesla. The frequency, this is the angular frequency. The frequency is equal to 60 hertz. Okay, the F. The second winding has 400 turns and it is left open circuit. So the value of the current in the second coil is 0. The stacking factor of the core is 0.95. The core, it means that the core occupies 95% of the gross core volume. Okay. So what is the stacking factor and why we use laminated cores for transformers? Here we stack up these electric steels. The explanation is available in the chapter 1. Here we have eddy current losses, and here we have this image. As you know, the aim of using laminated cores is to reduce eddy current loss. If we use a solid iron core, the amount of the eddy current loss will be high, so we will have a high amount of power loss, heat generated inside the core, and we should remove this heat from the core to ambient. That is very complex, and we should use laminated cores. And as you know, each laminations, right, are electrically insulated from the next lamination. So the equation that we have for eddy current losses here, and let me explain how using a laminated core we can reduce the amount of eddy current losses. Suppose we have this solid core, this one, and I want to just divide this solid core into two laminations. So here we have a solid core. This is solid, and this is laminated core. You know, for laminated electric steels, we can have these two types. This is a laminated electric steel with coating on one side. So this is, suppose this is one electric steel sheet. We can have coating on one side, or we can have coating, the insulation coating on both sides. So this is the cross section of the iron. Okay, this is the cross section of the iron, and we have coating here, or we can have coating on both sides, the insulation coating. This is the thickness of the iron, I, and this is the thickness of the coating, TC. Here in this case, we have thickness of the coating here. This is thickness of the iron and thickness of the coating here. The summation of the thickness of the iron and thickness of the coating is total thickness of the lamination. Okay. Also in this case, this is the thickness of the lamination. And what is the definition of the stacking factor or iron insulation ratio? This is the stacking factor or iron insulation ratio. This parameter is defined as follows. This is the thickness of the iron divided by the thickness of the iron plus the thickness of the coating. For the case 1, consider this as the case 1, and this is the case 2. In the case 2, we have coating, insulation coating on both sides, and we can write this is thickness of the iron divided by the thickness of the iron plus 2 times thickness of the coating. So this ratio is lower than 1, and we should consider this ratio when we calculate the reluctance of the iron, the reluctance of the core. Yes, to calculate the reluctance of this core, for example, we need to calculate the cross-section area, the cross-section area of the core. To use this equation, the reluctance is equal to L divided by the permeability times A. The A is the area of the net iron. You know, the magnetic permeability of the insulation material is like air. This is mu0, right? And we have flux in the iron part. The magnetic permeability of the iron part is high. So the area is the net area of the iron part, not the area of the iron plus the insulation coating. So the net area of the iron is equal to the area of the core, the cross-section area, times the iron insulation ratio, the stacking factor. Okay, so here is the case that we can calculate the reluctance of this laminated electric steel core right? And use it for calculation of the reluctance. But what is the reason why we use laminated cores and laminated electric steels to make the cores for transformers? Here, suppose we have a solid core and here we have a laminated core. In this case, I use the coating for one side only. So here is the coating material, and here we have iron, and this is a solid iron core. If we have a magnetic field, a time varying magnetic field like this, B, I want to calculate the amount of induced eddy currents in it. In this case also we have B and B here, time varying magnetic field. So in this case, when the magnetic field is varying, we have this, right, induced current in it according to the Lenz's law. And this is the streamline of right, one tube of eddy current induced in this solid core. So we know that the eddy current, right, is calculated using this Maxwell equation. Curl of E is equal to negative of partial derivative of B, right, with respect to time. What is the integral form? The integral form of this equation is this one. Integral of E dot dl on a closed path. This is the closed path that I considered in this solid iron, equal to negative of partial derivative with respect to time of this double integral b dot dA, this surface integral. So here is the closed path that I considered in this solid iron, and this surface integral, right, should be calculated on this cross section, the cross section of the loop that we considered. So finally, we can calculate E, the induced electric field in the iron, and what is the value of the J? The induced eddy current is sigma E. You remember these equations from electromagnetic course, right? Finally, when we have this eddy current, we can calculate the eddy current losses. Yes, you can write down the equations. So, what is important here is the area of this closed loop. In this case, as you can see here, we have a solid iron and the area of this closed loop is high. So the numerator of this fraction is high. And finally, the derivative is high. And the value of the induced eddy current, E, right, is high. The J, induced the electric field, is high, and consequently, we have a huge amount of eddy current in it. How we can reduce the amount of induced eddy currents? If we use laminated core and use insulation coating between laminations, we can, for example, in this case, divide the area enclosed by this eddy current. In this case, because we used two laminations, this is the loop of induced eddy currents in this electric steel sheet, and this is the loop that we have here. So in this case, we divided this area by 2, and we divided this, right, amount by 2. Consequently, the derivative is lower. The amount of induced electric field is lower, and we have a lower amount of eddy current in the core, in the laminated core. So using this method, we can reduce the total eddy current losses. In this case, yes, the thickness of the insulation coating will reduce the total thickness of the net iron a little bit. That is not important in compared with reduction of the eddy currents. So yes, this is how we can reduce the total eddy current losses. And consider that in this case, in the case of transformers, power transformers, distribution transformers, the frequency is even not too high, 50 hertz or 60 hertz. But in these cases, we have a high amount of eddy current, right? Losses is we use solid cores. So you can realize that how eddy current is important even for high frequencies. Okay. So in this problem, the value of the stacking factor is given, that is equal to 0.95. And here we have this number, the iron insulation ratio, Ki. What is the lamination thickness for practical electric steel sheets that we use for manufacturing of transformers or electric machines? We have these numbers. You can see these numbers in the data sheets, 0.65 millimeter, right? You can see how thin it is, or 0.5 millimeter, 0.35 millimeter, 0.27 millimeter, right? The thickness of the laminations that we use. Let's check one material in ANSYS Maxwell. For example, here, just I want to show you one material from the library. In the ANSYS Maxwell, we have the materials available produced by different manufacturers. For example, let's consider this M450A, this one. Okay, so let's check the material properties and what are these numbers and these letters. For example, here is the M450A. BH curve is at 50 hertz. So the BH curve that we have here is at 50 hertz. So what is this grade number M450A? We have two letters. These letters depend on the alloys and material, right? Materials used for the electric steel, the type that is oriented or non-oriented. Okay, so our focus is on these two numbers, this one and this one. This number is 100 times the thickness of the lamination. So what is the thickness of the lamination for this electric steel? Is 0.5 millimeter. This is in millimeter, thickness of the lamination. So 100 times 0.5 is 50. Okay, so this number represents the total lamination thickness, the lamination of the iron plus coating. What is this number? This number is given in watt per kg, or watt per meter cube. The loss density, loss density in terms of mass density or volume density measured at a specific value of B max. For example, 1.5 Tesla or 1 Tesla. Okay. So these two numbers are important, and you can check these numbers in the software or in the datasheet of the material. So here you can see the properties of this material, the HP curve. Let me select another one. This one. This is from another manufacturer, M450A. You can see the HP curve at 50 Hertz, and also this core loss model. Electric steel, you can see the hysteresis loss coefficient, eddy current loss coefficient, and other terms, right? Advanced methods for calculation of iron losses. Other terms that, right? You can read more about these terms later, right? In master or a PhD. So here, let's check the core loss versus frequency. As you can see, if we apply a sinusoidal magnetic field on this electric steel at different frequencies and different values of the flux density B max. For example, here is 1.2, and here we change the B max from 0 to 1.75. We have this loss data. This is for 50 Hertz, 100 Hertz, and so on. Here is the data sheet of this electric steel, and you can see the loss information. This is Tesla B, the B max. This is the excitation frequency, and as you can see here, when we increase the excitation frequency, we have more and more iron losses. This is ampere per meter, the H needed to build up this Tesla in the core. So what is the value of the for 50 Hertz and 1.5 Tesla? What is the value of the loss per kg? 3.89, close to 4. So 100 times that is 400. Okay. And you can now realize what these numbers are. Anyway, this just was a short introduction about the grades, what is the stacking factor, why we use a laminated core, and why we use coating between laminations to reduce eddy currents, and so on. More details is available in the next chapter when we discuss transformers. Okay, so you can read the next chapter, and this is the topic of the next chapter. Anyway, the cross-sectional area of the core is 25 centimeter square. So consider this term, the cross-section, not the cross-section of the net iron. So to calculate the cross-section of the net iron, we should multiply the stacking factor by 25 centimeter square. So I multiplied it by 10 to the power minus 4 to calculate it in meter, right, square. The permeability is 10,000 and the core length is 90 centimeter. So determine the RMS value of the applied voltage E1. In this case, just we apply a voltage on the primary coil or the coil 1, and we are going to build up this flux density in the core. So we can use this equation. You know, for one core problem, in general, we have this equation. So this is the coil, okay, and this is one core that we have. So we can write this equation. If we apply this voltage VI, this is the current. Let me write. This is the applied voltage. This is the current I, and we have this induced voltage in it. So we can write V equal to R I plus d lambda dt. D lambda dt is the EMF, or actually E. Okay, so what is R? R is the ohmic resistance of the coil. Lambda is the total flux linkage to this coil. If I neglect the resistance, the resistive drop, either considering a low resistance or a low current, right? If we neglect this term, the V is equal to the E, induce the voltage. And what is the E? The RMS value of the E is equal to 4.44 N1F by max. You remember this equation, right? From the previous problems, this one that we used. And here you can replace the numbers for the frequency, number of turns, the area, the cross-section area of the net iron B max. So we can calculate the amount of the applied voltage, that is 151.8 volt. So the next one, determine the current in the winding. So how we can calculate the current in the winding for the coil 1? Here we apply this voltage to the coil 1 V, and we have this B inside the core. How much is the value of the current? If we consider this mean flux line in the core, you remember, we can write this equation: integral of H dot dl is equal to N1 I1 in this case. So if we consider uniform field and simplify this integral, we can write H times L core is equal to Ni. And how much is the maximum current? So we know that here we have a sinusoidal, right, varying field. So we have a sinusoidal excitation for voltage, and we will have a sinusoidal current or not. Depends on the permeability of the core. So here in this case, we have a constant permeability. We don't have a nonlinear material. So the current waveform is purely sinusoidal. You remember also from this part of the chapter, okay? Here, when we have this flux phi, if we don't consider the hysteresis loop, and if we only consider the normal magnetization curve, this will be the waveform of the current. This one, I phi, the magnetizing current. So here, this is the fundamental component, but because here we have a nonlinear material, we have other, right, harmonics in it, odd harmonics, and we will have this waveform for the current. here you can see the phasor diagram also for the fundamental harmonic. And even if we consider hysteresis, the problem will be more complex, and this is the waveform of the magnetizing current. In this case, we have symmetry with respect to the point 7, but in this case, we don't have symmetry with respect to the point number 7. So, yes, because the permeability is constant, we have a straight BH curve. Consequently, we have a sinusoidal current. And how much is the maximum value of the current? We should consider H max. So, how much is the value of the H max? B is equal to mu H, and the value of the H max is equal to B max divided by permeability. So we have B max, that is 1.2 Tesla. We have the magnetic permeability, that is 10,000. We can calculate H max, and the mean length is given here, 90 centimeter. So we can calculate I max. Okay, the maximum value of the current. This current is needed to build up maximum value of 1.2 Tesla in the core. But we know that we have hysteresis loss, we have eddy current loss. Okay, we didn't discuss loss components because here, if you consider the case, we have this coil. This is V and this is I. This is the core that we have. The amount of the input power, Vi, is equal to the amount of the power loss. We have ohmic loss on the resistance of the coil, and also we have core losses. So this is the ohmic loss of this resistance and core loss that we have. Okay, so in this case, we should include the loss components in the value of the current. In the previous formulation, this one, integral of h dot dl equal to ni, we calculated the maximum current needed to build up the H max. But here, you remember this figure from the chapter that we need to include this core loss current in this current, the magnetizing current that we have. So we should include this term. So here is the part B, determine the current in the winding. We consider these assumptions, we neglect this, and just equivalently we calculate the maximum current counterpart to H max. Why I explain these details? So the aim of this problem is to review these concepts, and to answer these problems we should write, yes, considering this assumption, that assumption, right? We can calculate I1 max, right, using this equation. So these concepts are important and will be discussed in detail more in the next chapter. In the next chapter, we will include the effect of ohmic losses, core losses, when we generate the model of the transformer. Okay, so finally, what is the value of the E induced voltage in the second winding? Yes, the second winding is open circuit, and we can use the same equation like this to calculate the induced voltage. Here, just the number of turns is N2. And if you consider the numbers, the amount of the voltage is 303 volt. So using these assumptions, these simplifications, we can solve this important problem. You can review the chapter, review the points that we discussed, and review the solution procedure. Here, I generated this model to realize this number, right? To save the time, I generated model before, and let me open it. Okay, this is the model of the transformer I generated for this problem. Here, I considered the width of the core equal to 5 centimeter, the width of the yoke, this parameter that we have here. Let me copy this. Maybe you can generate the model and try the simulation. We did it multiple times before, and just to save the time, here, just I'm going to explain the parameters. This is the width of the yoke. I considered it equal to 5 centimeter. The depth of the core is 5 centimeter. So the gross area is 5 times 5, that is 25 centimeter square. The permeability of the core is 10,000. So in the Maxwell, I considered this iron material. The permeability of the core, the relative permeability is 10,000. And here, if we select all properties, we can set this parameter, the composition type. Is this a solid core or laminated? Yes, this is a laminated core. If we select this one, we should set the stacking factor. So what is the value of the stacking factor? 0.95, this number. Okay, 95%, 0.95. What is the stacking direction? The stacking direction, what is that? So here we have X, Y, and Z component of the coordinate system. Stacking is in the direction of the Z, right? So here we should select this one. Stacking is in the direction of V3, Z. X, Y, or Z is in the direction of Z. The cross section of the problem is in the XY plane. So perfect. How the ANSYS Maxwell software accepts these parameters. Okay. So the next dimension is the width of the window. I considered it equal to 19 centimeter, the width of the window. This is a square, and this is the same as this one. I have set the width of the window in such a way that I get this mean length for the average pass. So the average pass measure, the mean length is 96 centimeters, close to this one. Here we have 90. Okay. And you can change this number to adjust the average length pass equal to 90 centimeters. We have this polyline B here just to plot the flux density vectors on this line. That's all. We have this boundary condition. We have this current. This is N1I1, N1I1. This is N2I2. And also this one. Here we have the value of I1. I2 is 0. I1 is 0.429. The number that we calculated using these assumptions that we had, 0.429. And yes, let's run this simulation. Also here, I defined this matrix to calculate the amount of the flux linkage. If I run this simulation, we can check that is our formulation correct or not. Let's check. Here we have b vectors, and here we have the x component of the b on this edge close to 1.2 Tesla, right? So even you can select the core material and plug the magnitude of the flux density in it. So yes, as you can see, our calculations, our approximations are good, and we can get this amount of the flux density, the maximum amount, considering this Imax in the core. Okay, so you can repeat the same calculations. You can generate the ANSYS Maxwell model. Maybe you can change these dimensions and try other cases to learn the points of this problem. So now let's go for the next problem. Problem 21. The flux in the core of the magnetic system of this figure 17, varies with the time as shown in this figure 21, P1 21. The coil has 400 turns. Sketch the waveform of the induced voltage in the coil. So here we have the waveform of the flux in the core, the phi, and just we are going to calculate the value of the induced voltage. So just derivative of this function. The induced voltage in the coil is N times derivative of the phi with respect to the time. So this is the flux linkage. Okay, here we have this equation. V equal to Ri plus E. E is equal to d lambda dt. Lambda is equal to N times d phi dt. So how we can calculate derivative of this function? Derivative of this function, as you can see, the minimum, right, and maximum values, right, the peak values are the same. So we can write 2 times phi max divided by delta t. Delta t is the time span for each interval. So here you can consider this graph. You know that the derivative of this function is a square one, is this one, a square function. How much is the amplitude here? We need to calculate the slope of this function, right? The slope of this line and this line. Here the slope is positive and here the slope is negative. So here the value is N times 2 times phi max divided by the time span T1. This is the T1 and this is the T2. Here for this negative slope. So you can replace T1 and T2. We have phi max. Phi max is 1.2 times 10 to the power minus 3. So if you replace these numbers, we have this red curve. The value here, the induced voltage here is 115, and here is negative of 57. Yes, because here the slope is higher And here the slope is lower, the time span is higher, we have a lower amount of induced voltage. So this is the point of this problem. And let's solve this problem using simpler. However, the problem is simple, but I want to show how you can use simpler elements to generate these graphs. So let's close this project and rename this to, let's save it, 21, and let's add a simpler design. So how we can construct this function in simpler and how we can take derivative of it. Here in the basic elements you can use the blocks. Here we have continuous blocks. Here is the derivative one, the derivative block. And from the tools, time functions, we have various functions here. For example, pulse or sine wave, sawtooth. Let's select the data pairs. We have an arbitrary function and we can pass the data to construct this waveform. So the waveform is this one, and we are going to take the derivative of it. So here the name is data pairs, xy data. Let's define a new database, add, to generate the graph. So here you can pass the numbers. 0. What is the value of the y? Is equal to minus 1.2 times 10 to the power e minus 3. So I write minus 1.2 e minus 3. The next time point is this one. This is 1 divided by 120. Okay, so what is the value of 1 divided by 120? Format long is this number. This is 1.2 e minus 3. And the next point is 1 divided by 40. Okay, 1 divided by 40. The frequency of this waveform is 40 hertz, right? 1 divided by 40, 1 divided by 20, and so on. So here, what is the value of the 1 divided by 40? Is this one. So let's copy again, minus 1.2 e minus 3. So we have this waveform. The waveform is periodic. Okay, the waveform is periodic. The frequency of this waveform is 40 hertz. The period is 25 millisecond, the electric period of this waveform. Here we should consider the periodic, right? We should set that this data pair is periodic. So how we can set it? From here, you should activate this option. Is periodic? Yes. What is the period? Is 25 millisecond, the period of this waveform. So And we are going to, this is the flux. So let's change the name here. The flux. This is the derivative block. Okay. Here we have derivative gain, KD. In this derivative block, we have a function like this. KD derivative times df dt. F is the input function of this derivative block. And what is the value of the KD? In our case is 400, is the number of turns. So here, let's set this equal to 400. And that's all. In this case, we are doing a transient simulation. Okay, so we need to have a transient solver here. So this is a transient solver. We have three types of solvers. Transient solver in the time domain, DC solver, and AC solver. AC solver solves the model in the frequency space. Perfect software, perfect powerful software. Okay, so here let's set the simulation time. I am going to simulate two electric periods. So one electric period is 25 millisecond. Let's consider 50 milliseconds for the simulation time. And we need to specify time step, the minimum time step and maximum time step for the solver. So left this as is, 10 microsecond for the minimum time step and maximum time step 1 millisecond. So now let's run this transient solver analyze. Then we can generate these graphs. A standard report, rectangular plot, the flux function dot val. This is the output, the value of this flux function. Yes, this function that we defined, that we have here in this problem. And this is the EMF at trace. So derivative. Here, because the y-axis of these two functions is the same, we have this graph. But here you can select the flux.val and set the y-axis y1, diff.val y2. In this case, we have this axis for the the flux, and this for EMF. Much better visualization. So now if I add this X marker, the value of the EMF is 115 here, and let's move it here. The value of the induced voltage is negative 57 volts. So here are two levels. Okay, so you can repeat the same simulation in the Simplorer to calculate these waveforms. And also you can manually calculate the levels of the EMF and compare. So now let's go for the next problem. Problem 22. A 6-step voltage of frequency 60 Hz as shown in figure P122 is applied on a coil wound on a magnetic core. The coil has 500 turns. Find the maximum value of the flux and sketch the waveforms of voltage and flux as a function of time. So here, the waveform of the voltage is given. Okay, a 6-step voltage of frequency 60 hertz. This waveform is given, and we should calculate the flux. In this problem, the flux is known and we calculated EMF. And here we have EMF and we need to calculate the flux. So we should use integration. But there is one important point here. When we have this equation, okay, when we have this equation, this one, as you can see, when we have the EMF, the voltage, and we want to calculate the phi using this equation, when we perform integration, we will have this equation. The phi as a function of time is the phi at the time 0 plus integral of 0 up to t of this. We don't have any information about the phi 0. Okay, so we know that if we have a phi 0, for example, like this, suppose this is phi 0, but we don't know that, and start integration, right? Start integrating this function. As long as the voltage, the induced voltage, is positive, so we have increase in the value of the flux, and we can calculate the phi max right here, not the exact value, the difference between the phi max and the phi 0, right? So here we have a 6-step voltage waveform. Let me write, copy this. And as you can see, in this interval, right, the value of the E is positive. So we have 6 steps. 1 step here, 2, 3, 4, 5, 6. In the first 3 steps, the value of the voltage is positive, and we have increase in the value of the flux. The integral E divided by N dt, right? The cumulative integral here is increasing. Then we have this interval, and we have reduction in the value of the flux. The value of the E is negative here. So if we calculate this integral for this interval, we can calculate the flux function. Integrating is not too complex. How we can calculate the integral? Here we have this function. This is the time span 1. So phi for this time 1 divided by 360 is equal to phi 0 plus integral of from 0 to 1 divided by 360. This is the time. The unit of the t is second. E, that is equal to 45, right? Divided by the number of turns, n is equal to 500 turns, dt. The value of the function is constant, 45. So this is equal to phi 0. Okay. This is equal to phi 0 plus 45 divided by n times 1 divided by 360. This t1 time interval. Okay, so yes, you can do this calculation. And similarly, what is the value of the flux for this time? 1 divided by 180. This is phi in this time, 1 divided by 360, plus this integral from 1 divided by 360 to 180 e divided by n dt. So this is equal to this one, phi 1 divided by 360 plus what is the value of the e is 90 divided by n times what is the time interval here? T2. The time interval is the same. 1 divided by 180 minus 1 divided by 360. That is 1 divided by 360. The time interval is the same. So you can repeat these calculations to calculate the flux for this point, and so on. We know that because the value of the e is constant, its integral, right, is a linear function. So you can connect these points to build up this waveform, this orange one. But we don't know the value of the phi 0, and when we change the value of the phi 0, we can actually shift this function. We have multiple solutions, right? We have, for example, this solution, we have this solution, just shifting the same waveforms in the direction of the y-axis, depending on how much is the value of the phi 0 is. We can calculate the average value of this function and force that the average value is 0, right? So this is the case when we assume that we don't have any DC bias. DC bias in the flux, right? This I generated this waveform for this case, but in general we have multiple solutions. So I have set the value of the phi 0 in such a way that we have no bias in the flux waveform. This is my assumption. As you can see here, any problem has a point. However, this problem is simple and just we can do integration. But in this problem, the point is what is the value of the DC bias in the flux, right? And what is the value of the phi 0? We have multiple solutions. I generated this graph in the case that we don't have any DC bias. Okay, so now let's solve this problem in the ANSYS Simplorer software and also in MATLAB. I will explain here. Let's save as this project to project problem 22. So in this case, we need to use integration block. Okay, so here instead of derivative, let's use the blocks, continuous block, integrator. So here in this case, this is the EMF, and when we use integration, we can calculate the flux waveform. So we need to set the data set. Let's edit the data set. We have 6 steps. Okay, this is 45 according to this figure that we have. Let me copy this. According to this figure, we can build up this data set. So here the time is 0, and here we have this step. Okay, so as you can see here, in this case, we have this time and we have this step. So how we can model it in the simpler? Let me build up the data set using MATLAB and then import it here. So if I export this data set into desktop, my data, I want to show you the pattern that we exported data set. We have X data and Y data, okay, like this. So then we can import it in the ANSYS Simplorer. So here in MATLAB for the problem 22, we have these inputs. This is the frequency of the waveform, 60 Hertz. Okay. This is the electric period, one electric period, and this is the time interval for each step. That is T, the total electric period divided by 6. So we have these time points, and this is the value of the voltage for these time points. Here in MATLAB, we have this variable epsilon, right? A very low number. Or even you can consider epsilon and specify it yourself. For example, 1e minus 2. Okay, so what is this number? Here, when we are going to define data set for this pulse function, we can use this rise. So here the value is 45 and here is 90. From the numerical point of view that we are needed to use in the software, we don't have zero time for this rise. You need to consider a rise time, however, a very short one. So we can consider this epsilon, epsilon here and epsilon here. Okay, so you have the value of the waveform for these time points. As you can see, here I have a 0, t1 minus epsilon, t1 plus epsilon, and so on. Here are the next time points. And here are values. So if I run the code here, this is the value of t. Let's consider t transpose. And this is the value of v transpose. So t and v, we have this data. Let's copy and paste them in this notepad. Then let's check. Can we import this data set here for this function? Import the tab file, my data. Why we have something like this? Here is the x is the time point and y is the value of the voltage. So what is the reason? Here we have wrong inputs for the value of the t. What is the reason? This is the value of the t. As you can see, this number is negative, positive, negative. So what is this negative number? Here the value of the epsilon is too high that I consider it. So let me consider 1e minus 6 a very short number. So run the code again and construct this data. So again, I can copy and paste it here. So now let's import the data set. Tab file, my data. Yes, this is the function, the waveform that we have here, 45, 90, and so on. Okay. Yes. Is this waveform periodic? Yes. What is the period time? The frequency is 60. So the period time is this one, 16.66 millisecond. So yes, let's set the calculation time. This one, minimum time step 10 microsecond, maximum 1 millisecond. So now we can calculate this integral. So here we should divide this function by the number of terms. The number of terms is equal to 500. And what is the value of the integral gain? Is 1 divided by 500. Okay, so let's analyze to plot the graphs. Rectangular plot, this is the EMF value, this waveform, and this is the flux after integration. Again, let's select Y2 for this. So we have this variation for the voltage waveform and the flux. Okay, so now let's calculate the maximum values. The unit here is Weber. We can multiply this integral by 1e3 to just make the unit in milliweber. So as you can see here, the maximum is 1 milliweber, and here the minimum value, the minimum is 0. Okay, this is the maximum value of the voltage, the minimum value, and here are the maximum and minimum values for the flux. So yes, depending on the value of the phi 0, we can have multiple solutions. How we specify phi 0? Here in this integrator block, we have this parameter, initial value for t equal to 0. So the initial value, I considered it equal to 0. You can specify the initial value of the function. Yes. So this is important, and this is the point of this problem. If we don't consider any DC bias, we know that integral of phi over 1 electric period must be equal to 0. So here, for this function, if I calculate the average value is 0.5 milliweber, and I can shift down this function to make its average value 0, neglecting the DC bias. So here, if I consider 0.5 E minus 3, zero point 0.5 milliweber here, and rerun the analysis, integrator starts from the phi 0 and starts the calculation. So here, as you can see, we have this graph. Excuse me, here I should consider negative sign. I should shift the function down, not up. So as you can see, the average value of the flux is 0. Okay, the aim was to calculate minimum value of the flux and also the maximum value, the waveform. The minimum value is minus 0.5 milliweber, and this is the maximum value. The average value of this waveform in this case is 0. Yes, perfect. How we can use the ANSYS Maxwell software, how we should do settings, right? When we define this data set, we should consider that epsilon to define this graph, and we can use the integrator to generate these two waveforms. So we can solve this problem also in MATLAB. Here I defined these two vectors, the time and voltage. Here is the phi. Okay, I allocate the memory to calculate the value of phi for each time point. And here I used trapezoidal integration. This is the time points for 1 up to time I and corresponding values of the voltage. This for loop is actually this term of the right hand side of this equation. So when we run the code, we can calculate phi, and here I plot t versus phi minus the average value of the phi. So I make the DC bias of the flux equal to 0. So let's run the code again. Here you can see the waveform of the voltage and flux. Here I used y-axis command to plot the voltage, the left axis, and the flux numbers on the right axis. So we can generate this nice figure also in MATLAB. You can repeat the same calculation here and review the important point of this problem. Okay, what this problem says is that if we have this current, right, I, if the current has two components, IDC plus IAC, the DC component generates a DC flux and AC component generates a time varying flux. And this time varying flux induces the waveform of the voltage, this waveform, a time varying waveform for the voltage. So the DC flux, the derivative of the DC flux linkage is 0. EMF for that is 0. And we generated this graph, okay, considering this point that we don't have any DC bias in the coil current. So in this case, the minimum and maximum values are calculated equal to 0.5 milliweber, the maximum, and negative of zero point 0.5 milliweber for minimum. So, okay, anyway, you can review the questions we solved in this video, and let's continue solving the next problem in the next video. Thanks for watching.